So in this chapter, we are going to work with 2 samples instead of 1. This is the halfway point of the unit on hypothesis testing. So it serves us well if we think back, what did we do in the last chapter? Well, besides just learning how to take a hypothesis test, what we did is we had 1 sample, and that sample gave us an average, x bar, to test against the null hypothesis, or mu. Because the null hypothesis is basically stating some fact that we believe is true about mu, which in this case was the average of the entire population. So, in theory, if we take a small sample of that entire population, that small sample should match and not be statistically different from the mu. But in case that we found a rare event, an event that was smaller than our chance of making a type 1 error, we would then reject the null hypothesis. So that's what we did back in chapter 9. So what are we going to do in chapter 10? Well, we have 2 samples. And we're going to show you those samples as x bar sub 1 and x bar sub 2. So we're going to have 2 samples from the population, and most likely from the normal population, so we can run these proper tests. And these 2 populations have averages. And they, in theory, they should have the same average, or not statistically different. So what we now show, or we're trying to show in this chapter, is we're going to have these 2 samples, x bar sub 1 and x bar sub 2, to test if they are significantly different. That's what we're testing. Because in theory, the 2 groups should be the same, or according to the null hypothesis. The null hypothesis, in, I would say, 90% of your situations here, is going to be where the 2 groups' averages are the same. But if we have a rare event where one group is significantly different than the other, then, well, we have to reject the fact that both groups are the same. So what we are going to do now is run through the 4 types of problems that we're going to deal with in this unit. The first type is going to be called the t-type. The t-type is going to be chapter 10, section 1. And the t-type is when we have an well, I'll make that look a little nicer. It looks like unknown lowercase sigma. So we don't know in these t-type problems the standard deviation of the population. So if you are curious, what does the lowercase sigma stand for? That's the population's standard deviation. Now, what we will be given is the sample's standard deviation, or we will be given the raw data, and the raw data will then let us find that small standard deviation, or I should say small sample size standard deviation. So, t-types have relatively small sample sizes, and that means that if you take the sample of the first group plus the sample of the second group, so if there's, like, let's say 10 in the first group and 7 in the second group, these will be less than 30. If they were greater than or equal to 30, we would probably use a t-test instead of the t-type test. And these groups, of course, are independent, which means you can't belong to both groups at the same time. So the members of the first group, N, and the members of the second N group, they cannot be the same people. So these are independent groups. And this is especially nice if you want to test like maybe 2 towns and something within inside of those 2 towns. So the ends will not be the same, but also you could look at shopping malls or department stores or grocery stores, because the number of stores between those 2 relatively small towns won't get above 30 if you add both of them together. So that's a way you could do this kind of test. So that's the first video we're going to do right after this one, is do some t-type examples. The next is going to be the z-type. The z-type is when we have a known average. Sorry, not known average, a known standard deviation. And this is from the population right there. And it will literally say in the problem, this is the population standard deviation. I mean, just to kind of like wave it with a red flag. Another indicator is that your sample size will be greater than or equal to 30. So if your if your first group and your second group adds up to a number that's 30 or more, then more than likely you are going to be in this z-type problem. And of course, just like the one before it, this is also independent, because you can't have basically the same object in both groups. Now, for these really large n values, this would be good if you wanted to test 2 products. Let's say batteries. Are you kind of confused sometimes when you go to the grocery store and you have 2 different battery choices? I mean, like, which C-cell batteries am I going to buy? Well, you can run these tests, and you can run like one brand versus another brand. They're independent groups, and we can do that type of z-test to see if there's a significant difference or not. Okay, and the next one that you're familiar with is the percent comparison. And what's great about this is you can compare percentages between 2 groups. And of course, this is a binomial type comparison, because these percentages are going to be yes or no binary questions. You know, maybe a voting affiliation, or maybe a preference for a topic, whether you're pro or con something, or just you can even look at the percentages of those who have something or not, like maybe a cell phone or a video game system. But you can compare the 2 groups to see if they're different, which is kind of nice, because you can look at different groups from different states, counties, or different backgrounds. The percentage comparison, also known as the 2 proportional z-test, is pretty great. In this case, your n is your 2 groups are definitely going to have to be greater than or equal to 30, unless you're dealing with, you know, maybe a close to 50-50 situation. But I want to throw in the tests here, so your n sub 1, p sub 1, q sub 1 has to be greater than 10, and your n sub 2, p sub 2, q sub 2 has to be greater than 10. These rule of thumbs allow you to assume normality. And we'll run those tests in this independent group. These 2 groups will be independent of each other. You can't have someone be in 2 categories at the same time. Now, a little bit new to us here is going to be the before and after comparison t-test. Now, this is technically where we are going to take 2 groups, but in this case, this is dependent, because what we're going to do is we're going to do a before and after of that dependent group. This is incredibly important if we think about medical trials, because what we're not going to do is withhold a possibly life-curing drug and, you know, just let them not have it, you know, especially if they're ailing from something. So the dependent is really important, and also sometimes dependent trials, you have to try to implement something to a group that's being, you know, affected or not affected by something. So what we get to do here is we get to find the differences from the data, and we do that in a before after kind of way, and we'll talk about how we subtract in the order of that when we get to that section. And then we get to run a t-test. And the t-test is because we're going to have a sample size that's less than 30, because if I gave you a chart that was greater than or equal to 30, you'd spend all your time subtracting. Also, the t-test will be in single variable, okay? Which is a little kind of tricky, since this whole unit, by the time you get to this section in the book, you're going to realize that, oh, all I've been doing are these 2 sample tests. But this is technically going to be a 1 sample test because it's going to be seen that way, because we're doing a before and after of a dependent group. So even though the highlight is, a highlight of this chapter says hypothesis testing with 2 samples, it's really sampling the same group twice. So I know, it's tricky wording, but it still fits. Okay, well, that is the wrap-up of this introduction to 2 sample tests. Stick around for 2 sample t-tests.